Okay, well, this is our lesson on global climate change. It's a little bit of a big one because it's a very large subject to tackle. We're going to cover quite a lot, and this is broken into two parts. Uh, the history of climate change, we're going to cover the effects of climate change, how marine ecosystems are changing, and then we're going to talk about wind circulation as well. This might come up, I mean, every one of these might come up, but pay close attention to these because we don't just want to say that the climate is warming. We need to understand that the climate has consistently been changing throughout Earth's history, and there's several reasons for this. And we know about this through by geologic time. We'll talk about how we know this in a second, but we know that the Earth's eccentricity varies. It's interesting, according to Kepler's law, there is no planet that orbits a star in a perfect circle. And so actually it's a more of an oval shape, and the more ovally it is, the higher the eccentricity of its orbit. And this changes every 100,000 years or so, bringing us closer and further to the sun. But our tilt also changes as well, with a bit of a wobble. This is our obliquity, and this changes about every 40,000 years or so. So, yeah, it's never at exactly 23.5 degrees tilt. It will change every 40,000 years. So this leads to predictable variations in Earth's climate called Milankovitch cycles. So these are the Milankovitch cycles. And how do we know exactly that the climate has been changing? Well, we have three basic pieces of evidence. We have foraminiferous shells in ocean sediments. Different species have different temperature tolerances, and we see them when temperatures rise and fall fairly predictably. Air bubbles in the ice cores, they contain ancient atmospheric gases, and they can help us identify carbon dioxide levels and other levels of different gases in the air at that time. So if this was frozen 400,000 years ago, we have a picture of what the atmosphere was like 400,000 years ago. And not only that, the ice itself and oxygen within here. Um, what we have is we have isotopes oxygen 16 versus oxygen 18. Oxygen 18 has two more neutrons than oxygen 16. Um, Now, we can breathe both of these. It's perfectly fine. What's interesting, though, is we have higher concentrations of the isotope oxygen 18 when temperatures are higher, and we can use this to predictably identify temperature in the past, whether it was high or low. And all of these pieces of evidence line up to paint a picture for us over hundreds of thousands of years. So we have extensive data on this. Global ice ages followed by warmer periods occur roughly every 100,000 years. So we have our ice ages and then warmer periods. We call them interglacial periods. This is a strong correlation with temperature, but causality is not fully understood. Well, it doesn't mean what we know is not sufficient. We have quite a lot. We've just learned more. So we're going to cover this, what we know about this, and what we how we expect to see the planet change at this time. Typically, rising temperatures, not exactly everywhere, but in most places. Habitat and species loss, drought, soil desiccation, heat waves, increased precipitation in some regions. We've seen that hurricanes become not necessarily bigger, but also just much wetter. Rising sea level due to glacial and polar ice melt and thermal expansion. Don't forget thermal expansion and melting permafrost. Permanently frozen tundra soils that begin to thaw and release methane from anaerobic decomposition and carbon dioxide from aerobic decomposition. Um, and so we have under the soil, if you dig deep enough in the Arctic, you'll reach permanently frozen ice. So only a little bit above this is there soil that ever really thaws. But because of climate change, we're seeing this thaw a little deeper and deeper. So and this is a positive feedback loop you'll be asked to understand. As temperature rises, permafrost thaws. And as it thaws, it releases carbon dioxide and methane. But this methane, in turn, will increase temperature, causing more permafrost thawing and more release of methane and carbon dioxide. And this is our positive feedback loop. One phase encourages the other and encourages the other, and so on and so forth. Um, Now, the risk of global warming at 2 degrees. This is just a simple graph here, but it might not look like it. Key to impacts and risk: undetectable, moderate risk, high risk, very high risk. Now, what that means, that's what we're here to learn. But global mean surface temperature change relative to pre-industrial levels in degrees Celsius. So, if we see temperatures increase by 1 degree, our threats to ecosystems will be moderate. Extreme weather events will be moderate. We can predict them to be moderate. Large-scale events like ice sheet collapse will be moderate. But coral die-off is something that we expect to see really easily affected by climate change. So high to very high risk here. Arctic regions, we see moderate to high risk. Coastal flooding, moderate to high risk. River flooding, moderate to low. Crop yields, moderate. Heat-related morbidity and mortality, moderate, and impact on tourism, moderate to low. But if we get up to 2 degrees Celsius, which is quite scary, threatened ecosystems, very high risk for many of these. Coral die-off, very high. Arctic region impact, very high. Coastal flooding, very high. River flooding, high. Crop yields, moderate to high. Morbidity and mortality, moderate to high. Impacts on tourism, moderate. Uh, but yeah, we see quite extreme weather events, very high risk, large scale singular events, moderate to high risk. So yeah, this is an interesting graph here to really understand and know that there's data on all of these that we can dive into further. Um, so we're going to take a look at a few of these just very, very briefly here. But property loss, damage, potential relocation. Coastal communities, especially poor ones that can't build up, may need to relocate inland. Seawalls and other barriers can be built higher, but this does delay eventual flooding. So, um, yeah, this is a serious issue that we need to be aware of, and we should expect large-scale migration from coasts within the next 50 years, or maybe sooner. But we also have loss of barrier islands, which actually protect not just homes, but also ecosystems, salt marshes, and oyster reefs. Um, from wind and waves, these may be lost as well. So something to keep in mind here. This is an ecosystem service that may not be available to us. This is really fascinating. I want us to remember our Hadley cells. Hot air rises and loses its moisture, and cold air sinks. Right now, what's going to happen is we're going to see but we can predict the widening and weakening of Hadley cells. So as the temperature difference between the equator and the poles decreases, the air that's ascending and expanding from the equator travels further before sinking. All right. And what will that mean? This shifts subtropical zones like dry desert biomes towards the poles and expands the tropics. And this tropic region will expand northward, and we'll see these desert regions also expand northward. So regions between 30 and 60 degrees may experience drier climate as cool, dry, descending air from Hadley cells shifts north and shifts south. But we also have this really fascinating thing: the weakened, destabilized jet stream. So we have cold, contained Arctic air, and we have nice, warm air. But as we see the jet stream modified, as the Arctic will warm faster than other areas of Earth. The temperature difference between the equator and the pole weakens, and this will lead to, because of temperature and pressure differences between polar and subtropical regions, is what drives the polar jet stream. There's less of a difference between them. Remember that the Arctic is heating up at a rate that's much faster than the rest of the world, and the Antarctic as well. We'll cover that and explain why in a second. There's less of a difference, which means this jet stream is weaker and more wobbly, and so we can expect some drier climate conditions here in the West. But this polar weather, this polar air, will reach further down. We can predict this to happen in our region, which means even crazier, extreme cold spells. So climate change is quite wild, and might not have seen this coming. But yeah, winters can get a little crazier too. All right, so explain how the data above supports the hypothesis that the destabilized polar jet stream caused the cold spell seen in the Midwest. And just remember, you want to identify that the Arctic is heating up much more quickly than the rest of the world. And so the difference between the polar in subtropical regions is weaker. That's what drives our jet stream. So if we see less of a difference between these two, the jet stream itself will become weaker and wobblier and less stable. And so we can expect colder air to move south in the eastern part of the United States. And that's actually literally what had happened right here. This was January 6th, 2014. So, yeah, quite wild. Also, always use your data to explain where this is happening, right? Now, there's much more to be said about climate change. I'm going to just dive in here, but we're going to talk about ocean circulation. Specifically, we're going to cover the polar regions as well extensively throughout here. Okay, so marine ecosystems, altered range of marine ecosystems. Some new marine species, some new marine habitats will be forming by rising sea level, flooding coastlines. As you might predict, this will alter ranges for organisms. Some areas of the ocean will be too deep to receive sunlight, and the photic zone, that's the zone where sunlight can encourage photosynthesis, will shift up further from the ocean floor. Warm waters hold less oxygen, so many fish populations will decline or migrate to cooler waters. But we have maximum sustainable yield, which is interesting. We're seeing a dramatic decrease in Southeast Asia and in many places of the world. But there are some places where we're actually going to see changes that are beneficial to certain fish populations because it's the nature of climate change. Sometimes conditions are better for certain species and not for others. Now, the ocean circulation stuff is also quite scary and quite incredible. So, what we do know is we've known this for quite some time. We call this a thermohaline circulation. Warm water from the equator moves north and south towards the poles, and this is salty water. And once it gets too cold up here, it sinks and circulates throughout the oceans, and then rises as it warms up. And this is our thermohaline circulation. What this does is this brings warm water from the equator to regions of the poles. This is why England and Ireland have such moderate climates. It's because not only do they get a lot of rainfall, but they got a lot of warm water right here. This warm water warms up cold air that is moving towards it. So it doesn't really get too hot or too cold in the summer and winter. But what we're seeing here, which is pretty wild, this is also nutrients. Redistributes heat from the equator, salt and nutrients by mixing ocean water. So that's also important to know. But ice melt from Greenland is especially cold. So fresh water builds up in the North Atlantic, and this fresh water is less dense than salt water. So salt water will sink and sit below fresh water. So this prevents this sinking from occurring. This is one thing that we predict can happen and will happen. This cold North Atlantic slows warmer Gulf Stream waters, cooling Europe and slowing global thermohaline circulation. Now, if you look here, this is an important one. Land and ocean temperature percentiles 2014-2015 from National Oceanic and Atmospheric Administration, National Climate Data Center. Okay, so what is this here? Near average, not many changes. All right, so this is the white. Nothing has really changed too much in terms of climate change. Okay, warmer than average, colder than average. Well, it's obviously a lot more warmer than average, or much warmer than average. It's a large portion of this. Record warmest, all around here, the deep, deep red right here. Record warmest, Pacific Northwest, parts of Europe, all of this here. Now, cooler than average, much cooler than average. There are fewer instances of these, okay? But this would be the polar vortex weakening, possibly, right? But record coldest is right here. As we just said, the ice sheet from this is the second largest ice sheet. The largest one is in Antarctica, but right here, second largest ice sheet, we're seeing all of this ice melt dropping right in here. So all that warm water that's supposed to be reaching Ireland and England and the rest of Europe is not reaching it, or this might alter this experience of a more mild climate here. So this we can see clearly with certainty. Polar regions, I'd mentioned, they're warming faster. And remember, this creates less of a difference between northern polar air and subtropical air. So the jet stream itself will be altered. But especially in the Arctic with the North Pole because there's more land. I mean, there is Antarctica down here, but it is completely covered in ice, or mostly covered in ice. So this has a much lower albedo, a much higher albedo down here. But the Arctic especially is heating up much more quickly. There's more land and less water to absorb heat. If water absorbs heat, that's a lot better. But land does not have a high specific heat, so it will change temperature quite rapidly. It also has a lower albedo. Here we have ice with a really high albedo, and as our ice sheets melt, um, we have less reflection. So ice itself has about a 90% to 100% albedo and reflect the sunlight back into space. Unfortunately, water does not. Water will absorb a lot of sunlight and convert it into heat. Um, so that is a positive feedback loop. As temperature rises, more ice melts. As ice melts, more water is exposed, which absorbs more heat. And then that will cause temperatures to rise, more ice melts, etc. This is a positive feedback loop. So the Arctic has quite a few important positive feedback loops to discuss here. Distribution of tropical heat by poles, two poles by thermohaline circulation will also warm up these poles as well. So there's a lot going against the Arctic right here. And again, we also have this other positive feedback loop, melting of permafrost, permanently frozen tundra soils that begin to thaw and release methane. As this occurs, temperatures rise, more permafrost thaws, more methane is released, etc., 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 etc. All right. What's also interesting is air pollution. It adds soot and other particulate matter to the atmosphere and is distributed to the poles by atmospheric circulation. And just to give you a sense of this, here is ice. Darker soot and particulate matter covered ice absorbs more heat due to a lower albedo. And take a look at this picture right here. This is ice, not what you would expect. This looks like concrete. There's going to be a lot more absorption of sunlight and conversion of that into just heat and infrared radiation. So that the air pollution itself is changing the albedo of ice itself and lowering its albedo effect, which is quite wild. So a lot going against the Arctic in terms of climate change. Now, habitat loss and changes in habitat. Um, the polar bear is just a great example of this, but there's a lot that's occurring here. And the one that's not really looked at much is algae that actually grows. If you were to scuba dive under Arctic sea ice, you would see algae actually like sort of frozen or trapped in the ice, but it's thriving. It's surviving right here. So this is the base of a food chain, and that will, could cause the collapse of the food chain itself. Now, the ice itself is also used for hunting and for survival for seals. Certain seals will use this to get air, use these holes in the ice to get air. And polar bears are adapted to pounce, and this is how they hunt. There's no other real strong means for them to be getting these resources, right? So as the ice melts, this hunting habitat disappears from the polar bear, tertiary top predator species, and our primary producers also are losing habitat as well. So you might be asked to explain how the data above supports the hypothesis that destabilization, polar jet stream caused the cold spell. Yes, so this comes up regularly. Don't be surprised if you see this right here. Just remember, you need to know reasons why the Arctic is heating up faster than the rest of the world. One is the melting of permafrost is a positive feedback loop. The other is the melting of sea ice, which creates another positive feedback loop. And you also have pollution, which is covering existing sea ice, which decreases its albedo effect and increases the absorption of sunlight and conversion of that into infrared radiation. All of this heat causes the Arctic to heat up much faster than subtropical regions, causing the differences between the two to be less stark. And therefore, the polar jet stream, which depends on those differences, becomes much weaker. And will be altered, and we'll send cold air down to regions. And one of the regions that we'll be experiencing this is the Midwest and the Eastern United States. So, even though we may be seeing temperatures get a lot warmer, we may also be seeing a lot of extreme cold weather events in our winter. So, well, there you go. It's a complicated issue, but there's a lot to understand there.